방송 시작해도
네.
될까요?
네.
Hi everyone, welcome to the APCTP String Lecture Series. This is the the last lecture by Professor Euihun Joung from Kyunghee University. He will continue to teach the Coadjoint orbits and the dual pair correspondence. Please join me in welcoming Euihun.
Okay, thank you. So in the previous lecture, we looked at the classical aspect, or line particle aspects of this dual pair correspondence, how it emerges from these Coadjoint actions. And then in this lecture, we will consider the quantum versions, which is nothing but actually the representation side. So in this way, I will talk quite many things about representations. So we all learned when we learned QFT, the representations of Poincare group, and then maybe many of you were familiar with this representation, irreducible representations of conformal group, because in now CFT, those are quite important concepts. They're important. But more generally, we can also consider many other things like representations of spinning particles, spinous fields in ADS space or GS space, and also many other exotic representations which were discussed in many different contexts. So those representations are all infinite dimensional, clearly, because it's representations of non-compact group, which is isometric group in our cases. So in case of digital group, we know that it's not even some sort of discrete. There is energy is not bounded from below, and then those are typically what is called the principal series representations. While in ADS, what is called the relevant representations is typically what is called as discrete series representations. So I will show that how using this dual pair correspondence by quantizing it in a relatively trivial manner, we obtain all those representations. In a sense that effectively we get all possible representation which appears in physics in this way. So there is some sort of interesting and remarkable features of this. And maybe one other comment is that this was already in a sense studied. Maybe okay, I will postpone this comment too. So now let us move to the quantum versions. Then for that, probably you would need to quantize this Coadjoint orbit, either geometric quantization or maybe some other quantizations. That's one way. Or since we have a particle action, you can just follow usual past integral formulations and introduce some ghost in case of this constraint system, because we have gauge symmetry. But what we can do more easily is that we know that anyway, this is simple. To begin with, what we can notice is this is simple PQ system, just flat space. So we can easily quantize this one and then impose a proper amount of constraint as from the dual space, from the dual group. So in this way, we can simplify somehow discussions, and mathematically this is even simpler. So we have I will explain instead of this. So quantizations. So we know that quantizations of this PI, QI, PI is what? So this is, I told you that this is nothing but R2N by T2, it's a minimal orbit. So this is, if we quantize, then this is just what we all know, just Schrödinger equations or Fock space. So it's like, in terms of Fock space, it's nothing but an oscillator Fock space. Fock space. But then this n oscillator Fock space is nothing but representations of SP2NR actually. This is an irrep of SP2NR. So which irrep? This is what is called minimal representation. The terminology is clear, right? Because I told you that this space itself is a minimal orbit, and then the representation related to associated with this orbit is what is called the minimal representations. But in short, it's something just obvious for physicists. It's just Fock space representations. And then here SP2NR is nothing but some quadratic oscillators, all possible quadratic operator in oscillators. So then what we can do is that, so this is a global thing. And then there is a group orbit G times G prime. So if we quantize these orbits, then what we get is that on G irrep times on G prime irrep. So this is G irrep and then G prime. Again, this is 1-to-1. So the quantum analog of these pictures, entire space, I mean this phase space is foliated by this the kind of product orbits, is nothing but this Fock space, say F, which is a specific representation called the minimal representations of SP2NR, is now just decomposed in terms of when we decompose into G times G prime irreducible representations, we do have this decomposition here, and then lambda. There appear many representation label, so many different representations of G, but it appears together with some G prime representations, and then the pairing is unique 1-to-1. So in this way we can define an invertible map zeta, and when some label, then so zeta is a relating label for G representations to label for G prime representation. In this way we call this zeta correspondence actually. So this is known, this kind of correspondence is known either zeta correspondence or dual pair correspondence, reductive dual pair correspondence. Or duality. So just you just technically it's easy that you want to construct certain representations of G, then it will appear as a part of your Fock space, but together with some other representations of G prime. Again, it will be easier to begin with some example, which is a super simple thing that you all know. So SU2 is given by two set of oscillator, B dagger B, and J plus is A dagger B, and J minus is B dagger A. So there is the two oscillator realizations of your oscillator. Then there is another number operator, which in this case it turned out that it is U1 number operator. Let's call it N even. N is A dagger A plus B dagger B. So they mutually commute, and then you can realize in the two oscillator Fock space AB of so you have two oscillator Fock space. Entire this two oscillator Fock space can be decomposed into fixed oscillator number space, oscillator number 1 excitation or 2 excitation, together with A and B. And then each space, so okay, let's see. The Fock space, maybe let me write this as W. That's more. Here W. So in this case, W is just spanned by like A dagger and B dagger 0, right? And then W can be decomposed by some n to infinity, where the Wn and Wn is an oscillator. Sometimes I feel like n times is n Wn. So then Wn itself is what? Wn itself is some space of a fixed number of oscillators, right? And that carries the representations of SU2. So how did I write SU2? As well as representations of U1. In this case, U1 representation is one-dimensional, so it's trivial. So it's just it doesn't add the dimensionality of the whole space. So this is n, so it's a number n, while SU2 is n plus one dimensional or like symmetric n. So in this case, I will just put n. So we have this. So this is nothing but what is known as Jordan-Schwinger. So in a sense that we generalize this setup to many other cases. So let's go to more general setting. So then let us just resume the discussions just from very beginning. So we want that quantization of the minimal orbit of SP2NR, and then this coordinate of minimal orbit of SP2NR has 2n coordinate.
Can I ask a question?
Yeah, sure. Yeah.
So in the when we studied this representation of the UN, we also used this I forgot the name, so Schur-Weil duality or something like so.
Yes, that's essentially the same kind of thing.
Is it exactly the same? So or like is it some special case of this duality, or just they share the same some feature? The result looks very similar, so that
essentially the idea is essentially the same.
Idea is same.
Yeah, and then I don't know precise definition. I don't remember now precise definitions of Schur-Weil duality. So,
but this decomposition is the final result.
That's essentially the same idea. Yeah. But here the context is, I think this whole duality or reductive dual pair correspondence is more a bit stronger or a bit confined, because here we specify representations, underlying representation to decompose, and then also the two groups that. Yeah, sorry. Yeah, this is terrible. Each time there is an update of your smart devices, you don't know how to control it anymore. I don't know. It's different system now. You cannot turn off usually. Yeah, so it's essentially the same idea, but I think here it's more specific. So we define the context in a more strongly. Probably that's the difference. But essentially it's the same thing. If you have two groups, it's mutually commuting, then there is some this anyways, yeah, there is this term which is relating these two presentations. So yeah, one simple analogy of that is indeed any UN group representation is described by Young diagram, which is actually representations of symmetric group. And symmetric group and then UN group in these cases is acting on the tensor space, tensor representations of fundamental, which is, and then they mutually commute. And then it's the same idea. Okay, so then, so this is the orbits, the coordinate system of this minimal orbit. And then in this case, we have the Poisson bracket, because we have symplectic structures. With that, we do have this Poisson bracket. And clearly, this is what I'm saying is nothing but just xi and pi here. And then xi, pi, and then delta ij. So here I used the coordinate y to make a contact with my first lectures. That was precisely the coordinate system, which was used to describe higher spin algebra, but that's actually just x and p. And we know that quantizations of x, quantization will be simply replace x p by that, and then with just commuting. So just trivial stuff, huh? IJ. And in this setup, so SP2N is how it is, as I said in words many times, it's spanned by or bilinear. Xi, xj, and xi, and pj, and pi, and pj, like that. And then now we can, so starting from the minimal orbit, we can construct minimal representations, which I already told you, but let me repeat. Representations. So that's called also metaplastic representations. Even though this is, in a sense, the most familiar representations, or the most familiar, one of the most familiar sort of Hilbert space that you know, but it's very unusual, guys, actually, from the representation theory point of view. So there is two ways to get describe this guy's representation. Here only operator. So now we need to define Hilbert space where this operator acts. One thing is Schrödinger, what is called Schrödinger model is nothing but it's a position or momentum space with the usual L2 norm, and then other thing is Fock space. Fock model, sometimes called Fock model. So that's from now on I will drop the head from the operator. Otherwise it will be too complicated. And then dagger is I will take this convention tilde. And then I have AI A tilde J, which is delta Ij. And then your Fock space again is generated by some sort of AI 1 to n. Yeah, so number, and then etc. etc. Yeah, maybe let me take this example like that. So the reason that I emphasize this is that this is very familiar, and that there is nothing deep, probably according to how you think. But actually, this is very non-trivial if you go to representation theory, because we when we think in terms of just quantum mechanics, this is very triviality, because it's almost same thing, because even ground state here, Fock space, this is Gaussian functions, and you know all the relations. But if you move to more non-trivial representations, theory of G or G prime, which can be embedded inside of SP2 and R, actually that is very complicated. Spatial function appears in this Schrödinger model, while Fock model is relatively simple. Or in the other hand, Fock model is very complicated, the whole coherent state system. It's infinite excitations of oscillator, while Schrödinger model is some sort of homogeneous functions or something like that. So it's all the time, one sometimes it becomes very simple and the other is very complicated, and vice versa. And depending on how you choose it, you can really save a lot of computational effort.
Does it also relate to some boundary condition of the wave function?
Boundary conditions of the wave functions.
Like a wave function, I mean, yeah. So this wave function Schrödinger, maybe you can consider some plane wave and so on, but the Fock model maybe at infinity.
Yeah, I don't know actually. I'm not very sure. I'm not very sure.
Okay.
Not so sure. Actually, so what is also interesting in this whole duality constructions, that you will get a lot of representations as particular wave functions, which is not normalizable. That's typically the case in the principal series. That's in a sense very not surprising, because actually the labor of your representations is continuous. Then suppose that you have inner product between two representation with a different label. Then it should be there should be some sort of a delta, but now it becomes not a Kronecker delta because the label itself is continuous. Then you need to put the Dirac delta.
And then, what about the Schrödinger model inner box? So is it also has some problem difficulty there?
So that we cannot consider in this setup, because here you see that so you are reasoning from the usual quantum mechanics point of view, and then you, depending on the model, you change your space. In a box means that your wave function in a interval, right? Not in entire arc. But here we begin with the other perspectives. We consider this X space as a half of particular, in technical term, particular polarizations of this phase space, which is a nilpotent orbit of sp2 and R. Or if you like,
can you like imposing like you can consider like a discrete translation, and the move you can model out this your phase space with that. Not the whole, but the some.
Might be, but that I don't know. Yeah, I don't know. So here I will talk only Lie group things. Okay. So sp2 and R contains two mutually committing reductive Lie group. That's the setup that I'm considering here. But in principle, this setup can be generalized to many different cases where the other side, one side we have a finite group and the other side maybe not, and even more exotic group. So in that case, maybe there might be some possibility to include the situations like you described.
Okay, thank you.
Yeah. Okay, so this is the minimal representations, and which is Metaplastic representations. This is actually something I didn't really appreciate peculiarity of these representations, because actually this is specific representations of sp2r, which is actually double cover of sp2r. So, but in terms of SO1, 2, which is identical as sp2 or SL2r or sp2r. So sp2r or SL2r or sp2r is double cover of SO1, 2. But this Metaplastic representation only works for the double cover of sp2r. So in terms of SO1, 2, it's a quadruple cover. So it's a bit, if you start to think in terms of representation, it's a relatively unusual guy. And then, okay, now let us take the one simple example of this duality, which is this one, sp2nr. Inside, we know that sp2nr. Oops, this is not good. sp2nr. So this is actually commute with, there is O1, which is sending ya to minus ya. And then, so then in this way, we can decompose according to the representations of O1, the representation of a minimal representation. So, but since O1, this is simple G2, which is essentially just G2. There is only two representations. So that means that actually this Fock space, the minimal, what is called minimal representation in a proper sense, not metaplastic sense, but in the symplectic sense, there is two representations. So that the entire W Fock space is just decomposed even and odd, essentially even oscillator excitations or odd oscillator excitations, and it decomposed into these two pieces, which is a decomposition according to this O1. And then indeed, even representation and odd representation is both irreducible representations of sp2nr. So this is the simple example. Yeah, so I will just mention all these examples like this, because otherwise I think I could not find good way to deliver the sort of the juice of this dual pair correspondence within 1 hour. So I decided to go example by example like that. And then we can consider also the natural generalizations of a Schwinger model, Jordan-Schwinger model, which is this one. UM and UN are both dual, mutually commuting within SP 2MN and R. And here, the Lie algebra UM is described by AI, AJ, and UN is described by span by the other contractions. Sorry, here. A, I, B. So here clearly I index is running from 1 to M, and A index, AB index, AB index runs 1 to N. So in this way you have two copies of U, M, U, N. Here, this R means that you need to take the Hermitian combinations of this generator and then put the coefficient. Then what you can show is that actually your Fock space, so there is also global U1, which have a completely full contractions here. That's the entire number operator that again commutes with any all guys. And this U1 is also the U1 part of UM as well as the U1 part of this UN. And in this way, you can decompose the Fock space into, again, different oscillator number. And then each oscillator number, Fock space, can be further decomposed into different Young diagram. So say that if you have an oscillator, it will look like that. Yeah. So and then so this is there is no symmetry now among all those index, but you can just decompose into in terms of Young diagram, because there is essentially you see that the symmetric group acting on here, and then you can organize in terms of Young diagram. This Young diagram. So in this way, we can just say like all possible Young diagram of n boxes. You can define in this way. So in this way, what we know is that Wy, this carries specific Young diagram, means that either completely symmetrized or some partially symmetrized in a complicated manner, and then to form a certain other Young diagram. All those guys, each of those guys carries on the rep pi y Young diagram, and then there is some number here, and then here maybe I should put here on top. This is un, and then like that. Yeah. So here I need to explain a bit better. So by pi un and then y lambda, I mean that this is nothing but effectively in terms of SUN representation, this is just y, because we know that the SUN representation is given by Young diagram, and then the remaining U1 part is that the quantum number is given by lambda times n. Sorry. So here y number of boxes plus lambda times n. This is the U1 value. So maybe it's a bit too technical, but the idea is anyway. So this Young diagram, as well as this numbering m and n, completely fixes the representations of um and un. And then in this way, we can we know also the correspondence between these two representations. So we see that the correspondence of these two representations. So when so in this way, what we can do is that if we want to realize certain representations of, say, um in this Fock space, you just declare that actually the dual representation is un. So then you just fix the representation in the dual side. Yeah, I'm sorry that I cannot maybe provide more comprehensive
So here, what is n over 2 means?
So this is some technical thing here. Yeah.
I see. Okay.
Yeah, some technical thing here. There is some. Yeah, some technical things. So is different from by SUN, because you need to assign again U1 number. And then, so this is in a sense the most convenient way to handle the situations.
Yeah, I mean, factor 2 is just convention.
Here 1 over 2?
Yeah.
Not really convention, but it just comes from the oscillators.
Oscillator. Okay.
Compute in this way, and then it naturally arises like that. Actually, this 1 over 2 is important because of that. In many cases, actually, you don't describe really um in this way, and then actually you describe double cover of something like that. Yeah. I don't know. I'm saying correctly. So anyway, there is some issues of the covering because of 1/2. Because eigenvalue should be always integer, but here because of this 1/2, if I think the dual n is odd number, then I think you have some issue. So anyway, so here I took this example because we can clearly easily understand the map between two representations. So there is duality between this representation and this representation. The specific example of this is nothing but this Jordan-Schwinger. This representation and this representation, they are dual. So you fix this one and then you identify this. Here also the same. So then I will introduce what is known as seesaw dual pair. So actually, when you have a 2 sp2nr, then you can take two dual pair. Two dual pair. Such that G contains G tilde. So this flashes the in dual relations, while G tilde prime contains G prime. So this is this situation is called seesaw pairs. In this case, what happens is that again I will be sketchy, but if you take G representations and you branch to G prime, G tilde representation in this thing, because this subgroup, you can also always restrict the representation to subgroup. Then this representation will be dual to G prime and then pi G. So this kind of arrow should work. So maybe instead of just saying explaining in words, I think it will be easier again. Take example sp2nr with the O2, and then it's U2 and U1. So if you have this seesaw dual pair, then with the informations of this dual pair that we already looked, this is nothing but the Jordan-Schwinger model, you identify the representations of sp2nr associated with the O2, certain representations of O2. How do you do it? I know how to control the representations of O2, which is very simple. Just this integer number, L. And then I enlist all possible representations on this U side. That's already we handled. There is m1/2 U2. So I will have shorthand notations. So this I will take just y lambda UN. And then this is again this is m plus 1 and then U1. So these two representations will be dual. And then this I want to find out this representations of sp2nr associated with the dual to this L representations. But then what we can do is that okay, so L should appear, this representation should appear in the branching of this M representations. So then this tells us immediately that M should be, so by the way, this is M plus 1 U1 times M SU2. So it's a representation of SU2 side is M. And this O2 stays inside of SU2. So it's a typical branching of SU2 representation, spin J and like representation into the J3. So you can take O3 as J3, and this is entire things. Then M should be simply greater than L by certain even integer. So this is the possible. So if M is greater than L by some even integers, then this branching works. So this means that when in these branchings, so the representations of sp2 and R can be branched into these U1 representations with M, which is given by L plus 2n U1. And then n is from 0 to infinity. So this is specific representations of sp2 that we are trying to find in when we branch to U1. So this is what we get. And then actually this information alone is enough to classify this representation, because you see that the U1 is this U1 happens to be the maximal compact subgroup of sp2 and R, and then this U1 eigenvalue is has a lower bound. So this is a discrete series, lowest weight representation, highest weight representation. Yeah. So and then in this way you can immediately say that okay, indeed this is what is called highest weight representation, sp2 and r, sp2r. So here sp2, it's not 2 and r, so it's a simple example that I was. sp2 to r, and then the number is actually L plus 1. Lowest eigenvalue is L plus 1. So here it's L plus 1. Plus 1 is missing. Yeah. So in this way, I just identify the representations of sp2r by drawing these diagrams. And then maybe next example will be sp4 case, which is more physical and more interesting, maybe, which is again O1. This is already we looked, but we can do now. sp4. Maybe I can draw the. sp4 is the conformal group of three-dimensional conformal group, and then we have this U2, and then again here I have only plus minus sign, possible signs or 1. So to have a plus sign among representations like that, U1, M1/2, UN. In order to have plus signs, I need to have even M. So this tells that in order to have plus, I need to have even M, and then in order to have minus, I need to have plus or 1 is given by some sort of a 2n plus 1. M is even 1, and minus 1 is given by 2n plus 2. 1. So in this way, then these representations, plus representations of O1 is dual to sp4r representations, which can be decomposed in terms of U2 representations, like 2n plus, that's 2n, sorry, 2n. And then instead, this guy is 2n plus 1. And then it turned out that this is nothing but the representations, what we call conformal scala. And this is what is 1/3, and then 1/2 is conformal fermion, conformal spinor. Yeah. So this is in this way we can just identify the relevant representations of sp4r, which is a conformal group of three-dimensional conformal group, but the dual to O1. Then in this way we have two representation, which is a conformal spinor or conformal scala. Then we can ask whether, what are the other representations of sp4r? I mean, we can take other dual pair. I mean, bigger representation would need a bigger dual group, O2, for instance. If I take, again, there is another dual pair like this. And then here, again, the representation M1, U2, here, M1, U2. And O2 this representation is again decomposed by M SU2 times M plus 2 U1. And then say that I take here representation L of O2, Then again, the branching is that from SU2 to O2, and then we know that the M should be L plus 2N. Then in this way, we immediately see that the representation dual to L O2 is some direct sum n equal to 0 to infinity of this U2 representation, which is L plus 2N 1 U2. Sorry, U2. So this is what what is called the usual notations like that. So this is massless spin L. Sorry, massless spin. I think I should have here too. Massless spin 12 representations of massless spin 12 in AJS3, AJS4, or conserved current. Then current in CFG3. So all those representations, for instance, what appears in Vasilev's theory, all the spectrum, it just appears in this in this duality. So probably I'm a bit too quick and then a bit going to a bit too technical into this, but this is to show that actually many representation which is harder to understand in other way. Oops. What happened? Yeah, harder to obtain in the other way can be just understood in this way. Yeah. So even so, you know that the massless representation, you consider first some Verma module starting from some lowest waste state, and then you need to quotient, and then we need some submodule structures, and then always you construct in relatively many different rather complicated manner. But it turned out that most of this representation can be also realized within this dual pair correspondence just by properly choosing good dual group. And then the analysis of the group is fairly simple. And then interesting point is that this seems to cover effectively all representation, even principal 3 is one, and even any discrete, even some exotic representation like tachyonic representations. So what it doesn't seem to cover is the what is called complementary series representations. That's and also some representation with so this covers most of representation with the discrete label in the sense that because we are considering some honest SO2, D representations or some double cover, but quite often in physics we want to describe infinite cover. For instance, in conformal physics theory, we want to have infinite cover of SO2, D in order to have a conformal dimension arbitrary real number. Otherwise, it will be just to stick to some integer or half integer, like that kind of number. So in this setting, somehow we are still stick to some specific integer or half integer because we are really dealing with the SO2, D, or even in the other group cases, some specific really case. But probably that can be also relaxed, that kind of covering issue. And then maybe I have 10 minutes. So I will, even still it's a bit technical, but nevertheless, I want to mention one more example of this type to comment about something probably more interesting to many people. Is again this example, maybe we need first 4 dimensions, which is U2, 2, because SU2, 2 is nothing but SO2, 4. So this is a 4-dimensional conformal symmetry or 5-dimensional ADS symmetry. So if we take U1, then there is this dual pair. This is maximal compact subgroup is U2, U2, then it's dual U1, U1. Again, we know all these representations, M1/2, here N1/2, and here M+1. I omit the label for representations. And then eventually, let's say that we want representation L here. Then again, what we know is that M and N, I need to take actually so this M+1 minus N+1 should be L. I have this condition because that's just contraction diagonal restrictions. So in this way, we can easily see that the SUN U2, 2 representation is what is called what can be decomposed into U2 times U2 maximal compact this way. So this is what is called the L+1 and then L plus. So this is conformal spin L in CFT4 representations. Of course, it's only holistic plus L, but combining with the minus L, it just describes that one. So for instance, if you want to put the spin 1, then this will be the good one for describing gauge field in ADS, CFT4. Yeah. So in this way, what is interesting, maybe I cannot mention too much on this, but so as an example of this type is now I can take the same representation. I know these representations. If I take L here, then I get the spin L representation here. In particular, if I take 1 here, I will have a massless gauge field here. Then what I want to do is what I can decompose with the GL2C, which is Lorentz times the conformal weight. That will be GL1C. Yeah. And the GL1C is nothing but that is essentially can be viewed as the R plus times U1. This is a complex plane with a hole in it. So its radial direction is R and then angle direction is U1. So then actually this U1 just is this restriction. So it's this means that in this restriction, R plus representation is unrestricted, and representations of R plus is any real number, or if you like complex numbers. So any real number, sorry, any real. So in this way, so from this, what you know is that the L+1, say this just L, this massless spin L representation admit continuous decompositions. Say here the label is zeta, continuous decompositions, and then of Lorentz group, Lorentz representations, pi, pi GL2C, and then there is a zeta and M. So, yeah. So M should be specified. Yeah, M is L. Sorry. And then we know that from this side, we know that this is precisely principal series representation here. Actually, what is called the most degenerate principal series representations of SP2 and SP2C. And what is this? This is you decompose mesoid spinel into most degenerate principal series representations of Lorentz. So this is nothing but the celestial I don't know, celestial business. So actually most of many formula in this celestial CFT, and those are actually some concrete representations of concrete decompositions of some particular state in this representation can be always written as integral of a particular state here in terms of integral. So that precisely this. And another instance is that we know that U2, 2, I can put just the U1. U1 is in a sense a single guy, single spin 1, spin L guy, or spin 1 or whatever. But what I can do is that if I put U2, is effectively it's a two-particle state. It's intuitively. So then if I put the P, Q, then it can be understood as P incoming and Q outgoing particles. P incoming and Q outgoing particles. And then what I want to do is that I want to consider representations where P incoming spin mesoid spin 1 and then Q outgoing mesoid spin 1. So altogether P plus Q particles. And then I want to consider Lorentz subgroup of it, which is trivial. So what do I mean? I want to consider representation which has trivial Lorentz, but P incoming, Q outgoing. So this is scattering amplitude. And then, so this is the scattering amplitude, and then this is precisely realized like that. And then, so these representations, the representations of this side, where one of the GL side is trivial representation. Again, this side is given by what is called the most degenerate principal series representation. And it is well known that the most degenerate principal representation is described by functions on Grassmannian. So in this way, you see that Y scattering amplitude, you have a complex Grassmannian. And then also you know that in 4-dimensional complex Grassmannian and 3-dimensional real Grassmannian, and then in 6-dimension you have Coultonian Grassmannian. So or just so anything in a sense kinematic, any kinematic result, it look like most of kinematic result is used in theory in our business, can be effectively understood as with the dual pair correspondence. So what is also being understood, what I'm trying to also understand is that also ambient space formulations, Mellin amplitude, those should be also fall into this dual pair correspondence. It's effectively anything kinematic, and then anything about the formulations, simplifying expressions, and then finding the most useful variables, that boils down to this dual pair correspondence. Yeah, maybe I forgot to mention about this oscillator realizations of certain representation. That was in this HEP theory community, Gneidin worked a lot on it, and then in particular in the context of the supergravity, he constructed the various oscillator representations which provide the gravity sector and then Rarita-Schwinger fields and etc. etc. And then did many tensor product computations and a lot of things using oscillator. But somehow the aspect of this dual pair correspondence was not explicitly somehow. Implicitly he somehow used it, but it was not explored to its full value. Okay, so that's it. Thank you.
Thank you very much. Very interesting lectures. Please ask questions. I have a question. So this dual pair correspondence, you talk about the shift 3 and also shift 4. Can it be also used for the shift 2 so that you can cover some HS lambda and so on? So is there some possibility of some there, here you consider this presentation for the STEAM L, so that there, if you consider the shift 2 and the AGS3, there might be some representation.
Yeah, that I'm not sure. I mean, what we can do, and in the other dimension can be clearly done in CFT2. But we usually will not be satisfied with those results in CFT2. CFT2, because SL2R is extended to Virasoro, we can say much more things in CFT2. While in higher dimension, we only have conformal group, and then just people are exploring some basic kind of identities and or these properties of the representations of conformal group in a sense by doing this CFT analysis. So then much can be also done in the CFT2 using just SL2R and SL2R and using whole duality, blah, blah. We can try to do many things, but probably that will not give maybe more data than what we could extract from Virasoro things. So I don't know whether we can extend this whole duality to Virasoro. I mean, that seems to be doable, but I don't know how much it can give, how much useful result it can give. And about HS lambda, again, the same, even that's even more tricky. Because HS lambda, here you see that this is based on the fact that most of the classical group, actually all the classical group can be embedded inside of SP2NR and then in a quadratic manner. So that it's based on that. And in a sense, Virasoro can be okay because Virasoro can be effectively embedded in the SP infinity R because we have infinite number of oscillators. So whenever you know that a certain group can be realized as bilinear in oscillator, then this can be done. And then you can identify the dual group, and then you can do this job. But HS lambda, we don't know that this oscillator realization. So we don't know whether it can be embedded into any SP, blah, blah. Not that obvious. In principle, we don't need to embed inside of SP2NR actually. So people understood that actually this nice property will just work if we replace the embedding SP2NR into any group and then take instead of Metaplastic representation, any minimal representations of such embedding group. But the utility of this, the simplicity arises that minimal representations of symplectic group are particularly simple, just it's plain mode by Z2. Other minimal representation, minimal quadrant orbits are relatively, it's a bit more improved form. So that's in a sense what distinguishes this SP2NR.
Thank you. Any other question? If not, let's thank Professor Euihun Joung for the 3 hours very interesting lectures. I will stop the recording.